Jason, how are you? All fine?
Yes, sir. Yes, sir. All fine.
Yeah, great, great to see you back.
Thank you, sir.
How many are there? Only one?
Yes, sir. So far, only Dr. Joseph has joined, sir.
Yeah, we'll wait for some time. I'll just share my screen.
It's visible, sir.
It's okay, right?
Yes, sir. Absolutely.
Yeah. We'll just wait for 1 or 2 minutes. We'll start. And if the problem is, if people join later, they won't understand this whole thing. That's the problem. Or else we have to record it and they have to see it. First of all, thanks, Srinivasan. Thanks. I mean, are we holding you? I'm sorry that we're holding you. Is there anyone who can
Sir,
operate it?
not at all, sir. Not at all, sir. Absolutely no, sir. Please feel free, sir. Not at all, sir. It's my pleasure to be
No,
around.
no.
Not
You
at all,
have
sir.
so much of other things to do. I'm sorry. From next week onwards, we'll ask.
Sir, not at all, sir. Please, sir. Please, sir. No, no issues, sir. Not at all, sir. Please feel free.
Okay. I think we'll start, Josen. Arjun, I thought will join.
Okay, sir. Yes, sir.
At least if he joins another two people, then we can start. Can you call him? Is he away? I mean, is it that you forgot?
Okay, sir.
Sir, I consider it as a privilege to be a part of this group, sir.
Oh, no,
Anything with
no.
this flow
Don't use big
department, I
words,
don't want to miss
Srinivasan.
the opportunity, sir. So, no, sir, I mean it, sir. It is really a great opportunity to be with all these doctors, sir. I'm thankful that you are giving me a chance.
Oh, no,
I will, it's not at all an issue, sir.
no. Just thanks a lot. I hope others join. I think maybe they have not seen the message. I'll just check others. I'll just send individual mails, individual messages, sir.
Sir, he's Arjun
Dr.
is trying
Srinath,
to.
can you please share the link back in the group, the new group?
Yeah. So Arjun is trying to join. He probably is having some trouble with the net or something, but he's trying.
Oh, Dr. Shanti has joined. I'm just calling Dr. Sundar. Okay, once he joins, let us start. Sundar is not. Okay. We'll start. Arjun is anyway joining, right?
Yes, sir. Yes, sir.
Yeah. So let us go slightly deeper today into what we are doing. No MATLAB, but some concepts which will be very useful later on. So, I mean, we have covered quite a lot, in fact. So, let's just recapitulate what we have been doing. So, given a function f, we were calculating df by dx. So, in other words, we were looking at how actually the function travels in x, or how does it vary. For example, if you look at a function sine x, okay, so this blue line is the line sine x. Okay, so what were we looking at? We were looking at when it increases, when it reaches a maximum, when it decreases, and so on. So if you now really look at the sine x, for example, you can see that there is a slope. This is the slope. Okay, this blue line is the so this is that sine x function. So that function, okay, what is this has the largest slope at this point. What does it mean? It increases fastest. Then you would see that at this place, it slows down, it decreases. It reaches a maximum at this place. This is the maximum. And then it starts coming down. It comes down faster near this region and then goes down. And then again reaches the minimum here and then again travels up. Now, this is what we called as the df by dx, the rate of change of f. So this is what we said. I'm in a class, I'm taking a class. I'll call you later. Okay, so that's the thing. So I am plotting that change here. Look at that change. It looks very similar to this. In other words, this is sinusoidal, y is equal to sine x function. And this change, if I now plot, sorry. No, I'm in a class. I'm just taking a class, the maths class. I'll call you later. Yeah, but okay, sorry. So is that clear? So there is a positive slope, there's a negative slope, and that is captured by this thing. So on the other hand, if I now get df by dx, I have to get f. That is another part of it. Okay, we are going to see how to get that. So this is a function, this is a differential equation. So we can write, when I write df by dx, it is called differential equation, and find out f. So it is also, you can view it also as, which is, as a function which is going back. So then I'm going to other, yeah, df by dx. Then like this. So this is, if this is derivative, we will call this as anti-derivative. We'll see a number of things later. Don't worry about it. So this is how we give it. So many times we get only df by dx. When we will see that in a minute. Okay. So is that clear? So this is what we have been seeing, a number of functions. We'll go further on. So, but one, we have simplified the whole thing. So we have written, say, y is equal to x squared, or y is equal to sine x. So there is, these are, we have written it explicitly. We have written y explicitly. These are called explicit equation, explicit. Okay, so these are explicit equation. I won't be able to or there are situations where we won't be able to write this as an explicit equation. I may write an equation, okay, of the form, say, let's say, I mean, I'll write a complex equation. Let me not do that now. Let's say this. Let me write a complex equation. Let's say x power 4 plus y power 4 is equal to y sin x minus 7. Or just bringing this to the left-hand side, I can write x power 4 plus y power 4 minus y sin x. Don't worry about how complex it is. Just to make it more complex, I'm writing is equal to 0. Now, so this is quite a complex equation. And there's a big difference between y is equal to x squared and this equation. What is the difference? Here, actually, the equation can be written as y minus x squared is equal to 0. Even if you write like that, I can say, okay, fine. I can very easily write y is equal to x squared. And from which I can find out what is dy by dx, 2x. Very simple. But here, it is not easy for me to write y, not easy to write y as some function of x. How do I write it? That becomes complex. And I don't even want to attempt it. Such equations where I find it difficult to write y is equal to some function of x are called as implicit equations. Very common. Yeah, just one second. Dr. Sundar, are you joining? Yeah, please join. Yeah, sure. Okay, Dr. Sundar is also joining. It's been trying, it seems. So he's just. So in a nutshell, I have two equations. What are the type of? What are the type of equations? I have what is called as explicit. Okay, in which I'm writing y is equal to some function of x. Say y is equal to x squared. Explicit. The another equation is called implicit equations. In implicit, I won't be able to write it like this. So I will write like what I said here. I'll write it like this. Clear? Is that difference clear, Joseph?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Now I know how to do dy by dx for this. But how do I get how to do this? How to determine dy by dx for this expression? Because I don't have y is equal to something. Okay, if I'm able to write it, that is fine. Since I'm not able to write, sorry, if I'm not able to write, how do I now find out this expression? So that is the next step. So what I do is I differentiate each one of them. As Dr. Sundar joined, Srinivasan, Joseph, because I'm not able to see.
No, sir. No, sir.
Put a message on the other group. Kindly let me in, sir.
Oh, Srinivasan, can you let in people who are waiting?
Yes, sir. I look into that, sir. Yes, sir.
Yeah, we'll just wait for a second because this is important.
Sir, there is no one in the lobby, sir, and I have set it such that the lobby is also not needed. I'll check into that, sir.
think
So
I have some, he's in. He's in. Yeah.
it's okay?
Yes, sir. I joined, sir. No. Yes, sir.
Okay. So, Dr. Sundar, we have just been defining, sorry to repeat it because Dr. Sundar has joined. It will be difficult for him to follow. Let me repeat it. So, we said that there are two types of equations. Okay. So far,
Okay,
we
sir.
have been looking at one function, y is equal to
Okay.
function x. For example, y is equal to x squared. And then we were finding out dy by dx. Okay. Now, so essentially, we were looking at slopes, right? Is that clear? We were
Yes,
looking
sir.
at
Yes.
slopes.
Yes, sir.
Slopes. Now, so these are called explicit equations where y is equal to x squared. Explicitly, I'm writing y is equal to something. Okay.
Okay, sir.
So there can be an equation of this form.
Mhm.
In fact, unfortunately, there are a lot of equations which are as complex as this in
Yes, sir.
in our day-to-day work. For example, you will be surprised. A population. How what is the equation for growth of population? 2.8. I just picked it up. Power pt plus 3 p of tp is the population minus 7t is equal to 4t cubed. That is the equation. Quite difficult. So I will. I'll not deal with it now. Let me first see how to do this. So now, what is that I want? I want dy. Anyway, my goal is to get the slope dy by dx. Anyway, y, from a very difficult point of view, I can write y as a function of x, but I'm not going to do it. But without that, I want to find out dy by dx. Okay. For example, as I just now said, if I now want to, so if I now want the population, rate of growth of population, let us say I want rate of growth of population. So what is that I should find out? Joseph, what is that I should find out?
dp by dt.
dp by dt. Right?
Yes, sir.
So from this, anyway, that's what I want. So how do I do this? So I do it like this. Let's take this equation. X power 4 x power 4 is a function. Y is equal to x power 4. That's a function. So I write d by dx of x power 4. Right? Then plus, look at this carefully. D by dx of y power 4 is equal to d by dx of minus d by dx of y sin x plus d by dx of 7, okay, is equal to 0, because that is dy by dx of d0 by dx is 0. So this is the equation. So I'm saying, what are we doing? Every term in that implicit function, I'm going to differentiate it with respect to x. Is that clear? Every term I will differentiate it with respect to x. We have some simple formulas we already know. So for example, d by dx of x power 4. What is that?
4x cube.
4x cubed. Remember x power n x power n minus 1. Right? This is what we said. So now n is equal to 4. So 4x cubed. So the next term is d by dx of y power 4. Now I'm confused. D by dx of, because d by dx of x power 4 I know. but I don't know d by dx of y power 4. So how do I do this? This is done by, you remember last class we talked about chain rule. So it is a function of a function. So I say plus d by dy, because d by dy I know how to do it. d by dy of y power 4 into dy by dx. So now this is what we said as the chain rule. Right? So what is that? Again, I am repeating. Y is equal to x, which itself is a function of t. Okay. Then, so now look at this. Then if I now want to find out dy by dt, okay, then I write this as dy by dx into dx by dt. That's what I wrote. You remember? Okay. Now, let's look at this carefully. Take a minute. T is the independent variable, time. We will do a small problem in a minute. X is function of t. Y is a function of x. Look at that equation carefully. Y is a function of x, which is a function of t. So t is the independent variable about which I want the function y. What is the rate of variation of y? Is I want it with respect to t. So dy by dt is what I want. So dy by dt is equal to dy by dx. How y varies with respect to x? What is the slope of y with respect to x? So dy by dx. Multiplied by how x varies with respect to t. So dx by dt. So dy by dx is equal to, dy by dt is equal to dy by dx into dx by dt. I mean, you should not do this, but just to remember, it is as if you are, removing this dx, ultimately getting dy by dt. This we are going to see an example, very interesting example in a minute. But do you understand this? Is that okay?
Yes, sir.
Please stop me if
Yes,
you don't
sir.
understand.
Yes, sir.
Yeah. Dr. Sundar, Dr. Shanti, is that clear?
Yes, sir.
Yes, it's clear.
Yes, sir.
Yeah.
Yes, sir.
Yeah. Now, so the same thing I'm writing here. D by dy of y power 4 into dy by dx. Okay. Then I have y sin x. Next term. How do I do this? You remember that what is the rule I have to use? Product rule. So what is product rule? You remember that I have two functions. Say, for example, I have a function x sin x. This is equal to y. Now I want to find out y dy by dx. What did I say? First, d by dx of x, keep
Into
sin x constant, plus
d
x
by dx
into
of sin.
sin x, right?
Yes, sir.
This is what we say. Clear? This is the multiplication rule. Okay. Now, that's what I'm going to use here. So how do I write it? Can someone help me? This term?
dy by dx
Minus
Minus dy
by dx into sin x
minus y
into sin x.
minus sin x into
minus y cos x.
minus
Minus?
y into dy by dx of sin x.
Exactly. Understood?
Yes, sir.
So first I differentiate it with respect to y. So dy by dx. Keep the sin x constant. Then I differentiated y. Then differentiate sin x, keeping y constant. That's all. Very simple. Right. So what is d by dx of 7? 7 has no x at all. So that is just 0. Okay, is equal to 0. Now, let me rewrite this equation. First, 4x cubed. Okay, fine. That is there as it is. D by dy of y power 4. Just ulta, change x. So what
4y.
should this be? What should this be?
4y cube
4y cubed into dy by
dy.
dx. Right? Clear? Minus dy by dx is there. So let that be there. So minus sin x into dy by dx. Clear? Minus y is there. Let y be there. D by d of sin x, I just now said, see, d by dx, this is the formula. Just look at that. Sin x equal to cos x. Minus y cos x. Is that clear? Any questions?
For product rule and this rules, the variable can be different, like dy. For example, for y sin x.
I didn't understand. Yeah.
So
Hello?
y sin x. Hello. So it should be only working for x sin s, right? Like if it's different variable, also it works.
I don't understand.
So like,
there is y.
So product rule is function of x. One function of x multiplied by.
Let me understand this. You are talking about this guy.
Yes.
Okay. So it does not. It doesn't matter what the two terms are. It is d by dx. As long as y is a function of x, then dy by dx. That's what I want to find out. So dy by dx, right?
But we don't
I
know.
don't want that y. Just so I can use that as well. There's no problem.
But
clear.
But we haven't defined y as a function of x in this equation.
No, y. That is why I'm finding out dy by dx. Once I say find dy by dx.
Yeah.
Once I make that statement, dy by dx, y depends on x. That is what implicitly, that's what it means.
Okay.
Right?
Okay.
Is that clear?
Yes.
Yeah, 1 second, just 1 second. System. Give me a second. Yeah, okay. So is that clear? So dy by dx sin x. Okay. So sin x is cos x. So this is the equation. This is the equation. Don't worry about the independent result. You just, then I can rearrange that. So I will rearrange it. So I will get 4x cubed plus 4y cubed into dy by dx is equal to dy by dx sin x plus y cos x. This is what I'll get. I'm going to rearrange it. 4y cubed dy by dx minus, I'm going to bring this guy to the left. So when I cross over the equal to, I get a minus. So minus sin x into dy by dx is equal to y cos x. I'll keep it as it is. Okay, this fellow I'm going to bring it to the other side, minus 4x cubed, from which I can find out what is dy by dx. Okay, so this is 4 y cubed minus sin x is equal to y cos x minus 4x cubed. So dy by dx is equal to y cos x minus 4x cubed divided by 4y cubed minus x. Don't worry if looking at it very complex. Nothing. That's the rule. Simple rule. Okay. So now let us say x squared plus y squared is equal to 4. Simple equation. Help me to do this. I want dy by dx. You can rewrite it, but don't do it. Just so how do I write it? D by dx of x squared, right? Plus d by dx of y squared. Is equal to d by dx of 4. Clear? Is that clear? Arjun is there, right? He's joined.
Yes, sir. Yes, I'm here.
Is it clear?
Yes, sir.
Now help me. What
2x
would be the
plus
first term?
2x plus
2x plus
2y dy by dx
fantastic. Dy by dx
equal to 0.
0. That's all. So dy by dx. So 2 I will remove it. Is equal to minus
x by y.
Minus x by y.
That's all. That's all. You understood?
Yes, sir.
Okay. Now
Yes, sir.
let's do a problem. Okay. So we will study say tumor growth is what I want to look at. Okay. Yes. To study how buildup of fluid inside the skull, hydrocephalus. All of you are familiar with this. You this affects pressure with a growing tumor, right? I mean, the growing tumor, the pressure increases. So as the tumor grows, the volume grows, the radius changes. All right. So we want to find out how actually this is going to have an effect on the rates of growth or dV by dt. How is it going to grow? Let's look at that. Okay. As I explain, you will understand more about this problem. So first, I assume that tumor is inside the skull. So the tumor shape is sphere. And that's a valid assumption. Most of the tumors, brain tumors, are something like a sphere. So what is the volume of a sphere? Anyone? 4 by 3 pi
4 by
r.
3 pi r cube.
So r is the radius. Right. Now, with time, r varies and v varies. Clear? Which means that r is a function of t and v is a function of t. Clear?
Yes, sir.
Now, I want to first find out how does the volume change.
So
So
is
in other
v
words, I want.
so
Yes.
so v function of both r and t. So,
Yeah, correct. Ultimately, v is a function of r is a function of t. So in other words, v is a function. Okay, let me explicitly write it. Now, ultimately, t is the independent parameter. That's what I'm trying to say here. So v is a function of r, which is a function of t.
okay.
Clear?
Yes.
So How do I write now this equation for using this equation? I want to find out dV by dt. Clear? I want to find out dV by dt. The volume change. Right? Let me explicitly write it so that you will not get confused. Let me write it explicitly. What I mean by explicitly is V as a function of t is equal to 4 by 3 pi r cubed, where r is a function of t. So what do I want? What is that I want? I want dV by dt. Clear? I want dV by dt. How can someone help me? How do I do this? So 4 by 3 pi is constant. I'll keep it as it is. No problem. So that is 4 by 3 pi. That remains a constant.
Then it's d by dt of r cubed
D by dt of r cubed.
times dr by dt.
Yeah, so this is what I want to do. Clear?
Yes, sir.
D by dt of r cubed. So what is the rule I will use here? What is the rule I use here?
Chain rule.
Chain rule. Can someone help me with chain rule?
3r square times dr by dt.
ARDT.
dr by dt. This goes off 4 pi r squared dr by dt. So what does this tell you? Physically, can someone explain what it tells you?
This is surface area, right? 4 pi r square.
No, no, correct, but right. But can you tell me what this in English? What does this equation mean? How do you use it as a doctor?
Change of volume is directly proportional to the surface area of the tumor.
No, slightly more than that. So how do you use this equation as a doctor? Let me put it like that.
So you can just measure the head circumference. So you know
Yes, Shanti.
measure the head
Hello?
circumference. You measure the head circumference to get the size of the tumor approximate. I mean, of the fluid.
Yeah. So in other words, what you do is you measure. You take you know the the MRI scan and look at how it's very easy to find out how the radius of the tumor has changed over say a month. Okay, so let us say that it has changed by a certain amount, let's say 0.005 centimeter per month. It has changed. Now what this means is, if I now want to change, I want to look at how actually the volume is changed. Okay, let us say at that radius is 0.4, 4 pi into 0.4 whole square into 0.005 is how volume has changed. This is say 0.01 centimeter cubed per month. So that's how volume has changed. Is that clear? So this is the amount of volume actually that is displaced of the brain. That's how it has changed.
Yes, sir.
Right? So this is, so what you measure is one thing. I want the volume. Okay, so the volume can be determined like this, dV by dt. This is how you use it, say, for example, um, for any other thing, one function of a function. We see this all the time, where there are two variables. Both the variables are a function of, say, time. So then we connect these two. Any questions? Okay. No questions. Dr. Shanti, is this clear? How dr by dt is related to dv volume, dv by dt.
Yes, Mr.
Yeah. So now one of the important things for you is metabolic rates. Okay. So metabolic rate. Let's say that the metabolic rate is written as, let's say E is the metabolic rate. So E is measured in kilocalories, okay, per day. So metabolic rate, how do I mean, physiologically, how do I write this metabolic rate? So there is so kilocalories per day is what I'm consuming. So where are they consumed? In different tissues, right? So there can be, say, like 2, 3, 4 types of tissues which is consuming or which is responsible for the metabolic rate. Let us say E is a function of just two, for example, two types of tissues. Let's say whose masses are M1 and M2. Function of M1 and M2. Clear? The two tissues. There are, I mean, you can add M1, M2, M3 and all that. So let us say that two types of tissues, let's say M1 is equal to, say, 20 kg and M2 is equal to, say, 40 kg. Okay. Now, let us give an equation for this. E is equal to 140 M1. This is an equation which people have used for metabolic rates. There are more than two variables, so I'll just put only two. Plus 72.75. Right? So let's say, as I said just now, 20 and 40 kg. So I want to find out what is dE by dt. Okay, dE by dt. The change in the metabolic rate is what I want to find out. The metabolic rate is given by this equation. So someone is putting on weight, say M1, they may increase one type of tissue, or they may increase another type of tissue, say 40 kg, that may go up. So the fellow is putting on weight. Right? So I want to find out how would this metabolic rate vary? That's a question. You understood the question? What is dE by dt? Any clue? What is that you want to know? If I want to find out the metabolic rate, dE by change in metabolic rate, dE by dt. This is a change in metabolic rate. E itself is a metabolic rate, which means that it itself is the rate at which we use the energy. So it is kilocalories per day or hour or whatever it is. Let's say it is day, easier. How do I now find out this? Any clue? So you want to find out how this fellow is putting on weight. There are two types of tissues, say for example, they consume, the metabolic rates are different. How do you find out? Any clue? Is the question clear? That's the equation. So I'm just underlining.
Should be the rate of change of M1
Yeah. Hello.
M1 by dt.
Hello. It is the
It should be the rate of change of dm1 by dt.
brilliant.
That's the rate.
That's it. Brilliant. So I have to find out, if I want to find out d by dt, I have to find out, if this is the case, I have to get what is d1 m1 by dt and m2 dt. So how do I now express it? How do I now express it? So d by dt is equal to, can someone help me to do this? 140 is there, that's a constant, multiplied by m1 power 0.75.
So 0.75 into D.
Into
1 by
m. No, yeah, m. So 0.75 goes down.
Yeah.
m1
raised to
0.75 minus 1.
minus.
N is 0.7 minus 1.
Yeah.
Right?
Yeah.
Into, as Dr. Shanti said, it is dm1 by dt. Right? Because m1 is a function of t. T by dm1 into dm1 by dt. Clear? Plus 72 into 0.75 into m2 0.75 minus 1 into dm2 by dt. So d by dt is equal to these two. If I multiply 105 into m1 power minus 0.25 into dm1 by dt plus 54 into m2 into dm2 by dt. So this is the equation. m2 power minus point, sorry, 25. That's all. So there are two things. What is the mass of tissue 1, m1, which is say, what is the we had said 20 kg. This is mass goes here, multiplied by the rate at which this mass is growing. It is just, I can't multiply. This is very important thing is, I just can't say dm1 by dt plus dm2 by dt. No, you can't do that. The mass also enters the picture, and then the rate of variation of that mass, that also enters the picture. dm1 by dt, dm2 by dt. Is that clear? I'll stop for a minute. Just think about all that.
So you use the chain rule, right? Product rule.
Yes, exactly.
Okay.
Exactly. Any questions? Is that clear, Dr. Shanti? It's dm1 by dt is required, but we can't neglect what is the current mass. We used chain rule. We differentiated m1 with respect to m1 and then multiplied dm1 by dt. Okay? Any questions? Shall I go ahead?
Yes, sir.
Yes, sir.
Yeah. Okay. We'll do first. Let me today. I will with small problems. I'll explain the theory. Then we will next class. We will go into some problems before we go to what is called integration. Right. So I'm only slowly going. Look at it. If there's any questions, I will answer them. Okay. So this is a similar question. Okay. We will not do the question. We will just only understand the question. So the pollutant at a place X is given by this equation. So this is the pollutant, and these are, at different X's. This is X. That's the pollution. As you grow, as you go out, the pollution may be different. Clear? Now, someone is standing here. Okay. He or she runs away. Okay, at 4.8 meters per second. The question is, how does the pollution change as she runs? What is running away in this? What is an equation for running away? X is the distance. What is running away?
Velocity.
Velocity, correct? So what is velocity? Change of distance is dx by dt. So again, look at that equation. C as a function of x, since it's running away, is a function of t. Clear? So this is how it comes out. Do that as a problem. It's very interesting. I'll just leave it at that. That how various applications can come up with these kind of things. There are a number of them. Say, for example, there is a formula called Du Bois and Du Bois formula. Anyone heard about it? The Du Bois and Du Bois formula gives a relationship between body surface area to the height of the person and mass. We have used body surface area extensively in our work, especially in cardiac failure and so on. In fact, there are very interesting results we have got with body surface area. So body surface area is a function of both mass and height. So Du Bois and Du Bois formula says that the body surface area, BSA, body mass index people work, but scientifically most people use body surface area, is equal to 0.2 m power 0.425 h power 0.725. Oh, so that is the formula. Clear? So this is now the body surface area changes as a function of both the height and the mass. The question is, suppose a person is 1.8 meter tall, he has grown, he is not going to change. But he may gain weight or he may lose weight, whatever it is. Say 70 kg. He may. So, how does the body surface area change? Is the question. So, in other words, ds by dt. Okay, ds by dt is what I want to find out. How does it change? Rate of change of body surface area. She's putting on weight. He or she is putting on weight. So how do I write this? All of you know from the previous experience. So let me just get to the next page. So I've done it anyway. How do I do that? Any help? Just simple. I'm not going to work it out completely. Just
Use the product rule and chain rule.
yeah. So 0.2
into
into
0.425
0.425
into m.
dm by dt.
DM.
No, wait.
One,
M
0.425 minus 1.
minus 1, which is minus
5.575
575
into dm by dt.
dm dt. Is that all?
Times
Uh,
h power 0.725
H power 0.725
plus
plus
0.2 m.
The 0.2 will remain a constant.
Yeah,
M power
0.425
0.425
into 0.725 h
into H minus
275
0.75
into dh by dt.
into
DH by
fantastic.
dt.
So that is what it's actually. It looks complex, but it's nothing. Keep one constant, differentiate the other. So dh by dt. So this is how it varies. Clear? So if I say that the person has grown, he's not. I mean, he is 20 years old. He's not going to gain weight. So what? I mean, sorry, he's not going to gain height. So what do I do? How do I now reduce this formula?
dh by dt 0.
This becomes 0 because dh by dt is variation. That's going to be 0. So this whole thing goes off, and I have only up to this term. Right? Clear? Okay. We have given a number of examples. Okay. Any questions? Clear so far?
yes, sir.
Yes,
Yeah.
sir.
Dr. Shanti, anything I need to repeat? Is there any confusion?
I was just wondering why initially only it could have been made as a constant.
Yeah, but pardon?
Initially, the height component.
See, dh by dt, I just introduced it because it may, for a young person, it may vary. I mean, for a kid, it may vary. For a boy or girl, it may vary. So I introduced it. But then once dh by dt is equal to 0 for a grown-up person, so this term just goes down. Okay. So what, as a first rule, what I wanted to show you or tell you is that I can't just multiply this by dm by dt or dh by dt. You have to differentiate it, each term. That is what we are trying to tell. Does it answer your question, or is there any other question?
So the m in this formula is the m at that particular point of time, right?
Yeah.
Okay.
Okay. Physiologically, this is a very important formula. Okay. And we were wondering about body surface area and resistance to flow. You know, so body surface area is higher, means that, Dr. Sundar would say that the arterial tree will be more. There are so many more arteries, right? That is, the length of the artery will also be higher. Correct, Dr. Sundar?
Yes, sir. Yes, sir. Well,
Because
that we
body
used to
surface
know.
area is high.
Yeah.
Perfusion has
Yes.
to be there in all. Okay.
Yes.
There's a question I had asked initially.
Yeah.
So if the resistance is higher for a person with higher body surface area, then let us say his cardiac output is 5 liters per minute. Okay, if the resistance is higher, cardiac output is the same, 5 liters per minute. Okay, then for all people with higher body surface area, then his pressure will be, or systole minus diastole will be higher. Correct, Dr. Sundar?
Exactly, sir. Yes, sir.
Resistance is higher, but
Yes.
you don't,
Yes.
because his resistance to flow is higher.
Higher.
So his cardiac output is the same.
Same.
So his pressure has to be higher.
Higher. Yes, sir.
But so as the person weight increases, the thing is pressure should keep on increasing.
Exactly, sir. Yes, sir.
Right? But it doesn't happen.
Yes.
Okay, it doesn't happen. It's not necessary that if a person is tall or obese, that his blood pressure has to be much higher. It's not.
Yes.
Okay. So
Yes.
what happens? It's a very interesting thing. So we had data and we plotted this data. So if I now plot body surface area, usually if I now plot body surface area versus the resistance, if I now plot, you will expect that it will go on like this. It doesn't. Interestingly, it doesn't. So how is that it doesn't go on? Either it is almost a flat or even slightly decreasing. Why is this? So because of the fact that the arteries develop in parallel in order to reach all the whole of the body surface area. So they are all in parallel. So the resistance to flow when I have parallel arteries is lower than when the arteries are, of course, in series, and lower than even regular artery. So in other words, if I now include all the areas of these small arteries and then make one big artery, okay, the resistance of this, in fact, would be higher than this guy. So a parallel arteries, God, nature, whatever you want to call it, has given us arteries. As you develop your body, their mass and all these things, the arteries become parallel. So it doesn't affect the resistance. In fact, resistance may even come down a bit. And so the pressure is not affected. This was a revelation for me when we looked at body surface area. But we had a very interesting, so body surface area keeps dropping. So what is the effect actually? With body surface area, resistance keeps dropping. When we do this, we found that the organ perfusion pressures are lower, because many times the resistance actually drops. The organ perfusion pressure, mean perfusion pressure to the kidney is actually lower. So we were wondering what's happening. And in fact, when we looked at a heart failure patient's data, we found that when body surface area increases, the multi-organ failures are higher. Okay, so usually what would immediately you do is, oh, the flow resistance is high. It is because the body surface area is high, the resistance to flow is high, and hence the blood does not reach the end organs. So there's an end organ failure. This is what you will conclude. Actually, it's not like that. The resistance to flow is small, drops. Right? The resistance to flow drops. Because the resistance to flow drops, the pressure actually drops. Pressure drops. So now, this is interesting, Dr. Sundar. At this time, you give vasodilators. In heart failure patients, you give vasodilator. Especially for high BSA patients, when you give vasodilators, it dilates the arteries, especially the capillary arterioles and so on. Arterioles have maximum effect. Then the resistance actually drops further because of vasodilator.
Yes.
And so the mean perfusion pressure actually drops. So the kidney, for example, renal artery, the perfusion pressure further drops. And interestingly, the data which we have collected from MGM with Dr. Balakrishnan, it shows that more than the cardiac output, it is the perfusion pressure which is important for creatinine. In fact, there is a correlation between creatinine and the mean perfusion pressure, which we calculated by model, than cardiac output. So even if your cardiac output increases because of vasodilator, if your mean perfusion pressure drops, and we saw that more and more in biventricular failure, mean perfusion pressure drops, the organ failures are higher. Dr. Balakrishnan, jokingly told in one of our meetings to Dr. Ravichandran, who's the nephrologist, hey, no one dies because of my heart. Everyone ultimately dies because of you guys, the kidney failure. He was joking because actually that's what the data shows.
Yes.
In heart failure. So BSA is a very interesting factor. And how actually body adjusts to BSA is also very interesting.
Does the body compensatory mechanism was taken into account, sir? Like
yes.
if the
baroreceptors.
Yes.
Baroreceptors were modeled.
Yes.
Okay, so the heart rate gets adjusted.
Yes.
But in spite of it, the fundamental physiology of the vasodilators does not change. Okay,
because in heart failure we often see the release of counter-regulatory hormones, which often makes the systemic resistance more higher in order to maintain systemic resistance more will be more And those are all the things. If it is more, then the organ damage will be more, and multi-organ damage will be more. And
But if there is a if the vasoresistance increases,
yes,
okay, so there's a counter thing,
yes,
So say for example venous pressure, that
yes,
also has an effect, right?
yes, sir.
So central venous pressure is also affected.
Yes, sir.
So in spite of it, if
Yes,
the vasodilator beats that, as you said, compensatory mechanism,
yes,
which can be modeled,
yes,
then the end organ failures are higher.
yes, sir.
So that's a so we have to increase, especially biventricular failure. We have seen this, but what you say is absolutely right, because in the left ventricular failure alone, the data
Yes.
shows
Mm.
it does not. The end organ failures are much less because the mean perfusion pressure is not affected to that extent.
Yes, sir.
But when biventricular failure data,
Yes.
one day I'll show you we have just got a paper published in
Okay, sir.
Heart, Lung, and Circulation.
Okay.
I'll send it. I'll share it in this group. There we have seen this thing.
Okay,
So
sir.
so we had to explain it using a model. Why this is happening? A mathematical model. We had to explain.
Okay, sir.
Okay?
Actually, you mean to
So,
say that vasodilator, giving a vasodilator is going to harm the kidney, right?
yes,
Sir? It's like
yes. The data shows that also. A model also shows, especially biventricular function. When there's a biventricular failure. So what we did was, Dr. Bala suggested that why not we put a intra-aortic balloon pump, IRBP.
yes,
So
sir.
IRBP is a counterpulsating pump.
Yeah.
Okay. So that increases the pressure, but slightly drops the cardiac output. So when you use both together, especially in biventricular failure,
Okay, sir.
in fact, it was used in patients and used as a model. We found that it's a win-win. We had a better cardiac output and better also mean perfusion pressure.
Okay, sir.
Both of them were better.
Yes.
So, just an aside, because I thought I should share something.
Yes, sir. Yes.
Interesting.
Yes, sir.
Okay, so we will maybe later towards, not in this course, we can't do everything here, but later we will also show you how modeling is done. And actually, these results are corroborated by models as well as actual ICCU data. Out there corroborated.
Yes. Yes.
Okay.
Yeah. Sir.
So these are very I would say very interesting. When you see this has a lot of applications and very interesting. Okay, so there's one more application. Can someone think of this kind of applications? So the resistance to flow itself is proportional to 1 by R power 4. So let us say that it is some constant. So the resistance to flow in an artery is proportional to 1 by R power 4. Okay, length and so on. So this is the reason why this is the resistance. Smaller arteries, that's why, offers more resistance to flow. Right? So now I want to find out how does this resistance changes. See, for example, let me take Dr. Sundar is interested in velocity, right? Velocity of flow. Okay, right, sir, Dr. Sundar? So you are interested in
Yes, sir.
velocity of
Yes.
flow.
Yeah. Yes,
Okay.
sir. Yes, sir.
So let's say that velocity of flow, okay, is now proportional to two things, or is a function of, let me write it, not proportional, is equal to a function of the resistance, the radius r, okay, this radius r, and interestingly, the distance, let's say that this is small r. So the velocity, if I now, let me say this is the artery. Okay, the velocity is now, the velocity graph is something like this. This is the velocity graph. Sorry. That's the velocity graph. And is given by r, and so comma r. R is this distance. So V is equal to some constant into r squared minus r squared. This is the equation for velocity of flow. Okay.
The capital R is the diameter and small r is the radius.
No. Sorry, 1 minute. This is capital R. Okay. This is the center of the lumen. Okay. The distance from the lumen is small r. Clear? Distance from the lumen is small r. So in other words, what is the center at this point? What is r at that point? Say, let me call this as A. At A,
0.
0. Right?
Yes, sir.
R at this point, B. What is that?
R by 2. Capital R by 2.
Capital R by 2. Oh, okay. Let me call this as 2R. No, sorry. It is the radius is R. So this is 2R. So this is equal to R.
R.
Right?
Yes.
Okay. So the velocity at this point, what is the velocity? 0. Right?
Yeah.
Because R is equal to capital R squared minus capital R squared, 0. So where is the maximum velocity?
At A.
At A. That is K into R squared.
Yes, sir.
Okay.
Yes, sir.
Is it clear?
Yes, sir.
So this is how the velocity changes. So the resistance changes to proportional to 1 by r power 4. R is this radius. Okay. So if it is proportional to, let's say that V is equal to, what are the things that are involved? The K length, and then viscosity, all those things. Let me not go into those details. We will just see how we will say K is K divided by R power 4 is the resistance to flow. Resistance. Let me call it as RES. Now, there is a block that is building up. So in this equation, what's changing? R. Right? Clear?
Yes, sir.
Now, what do I mean by block is building up? dr by dt exists. Is that clear?
Yes, sir.
Yes, sir.
Now, let's see. This is a small problem. Let's see whether you answer this. Is equal to k r power minus 4. Correct? Is that correct? This
Yes.
plus 4 will become minus 4.
Yes, sir.
So how do I write DRES, resistance, by dt?
Minus 4k r cube dr by dt.
R
R
minus
minus
3.
five.
R4 minus 3.
Here.
dr by dt.
Okay.
Um,
Josen Arjun. Okay. We'll ask.
R is to minus 5, right?
R power minus 5, right?
Minus 5.
Sorry, minus 5. Right.
Yeah,
Minus
R4 minus
1,
5.
minus 1. 5. Yeah, minus 5. Okay. I was concentrating something else. Hey, but I have a problem.
Okay.
So this is one negative sign here. Right? There's a negative sign here. Now, what is this? Resistance changes with then building a block is good. Resistance is dropping. But that's not what we want. When there's a block builds up, I'm worried that there will be an increase in resistance, then flow gets this thing, fractional flow reserve, all those things come up. Now, how is that there's a negative sign here? And why am I worried about resistance change at all? The block is building up and the resistance is dropping. Fantastic for me. Understood the question? Dr. Sundar and others?
The pressure also should drop, then resistance.
No, we are
will
only
drop.
talking about resistance. Then only we go to pressure. So the resistance drops. It is good for me. For the same pressure, my flow will be better. Right? So the flow rate is the pressure, by that resistance. If the resistance drops, so P resistance into Q. Resistance drops or Q resistance drops, my Q will be good for the same pressure. So it's minus, but that's not what happens in practice. So what's the dichotomy here? What is the problem here?
Showing the direction or something like that.
Look at that carefully. Look at that, yeah. But look at that carefully and answer in English.
I think physiologically it should be kept constant, the flow, so the pressure
Hello?
should drop. Since Q should be auto-regulated, the pressure.
Sir, you are audible.
Dr. Shanti, I'm not able to hear you. But we are only looking at this equation. No other auto-regulation. Only this equation. So what is actually happening to R as block builds up?
Reduces.
So the diameter is actually coming down. So
Coming down. So what does that mean in that equation?
dr by
Is
dt
negative.
negative.
dr by dt is
Negative.
negative
Negative.
because radius is coming
Yes.
down. So
Yes,
this is
coming down.
negative.
So it becomes positive.
This negative becomes positive.
Positive. Yes. Yes.
Okay, you have to
Yes.
be careful in looking at this.
Yes.
Okay. So the problem is when this comes down, okay, the resistance, look at this, how it actually varies. There is now what was r power 4 has now become r power 5. Radius itself is coming down. That is r power minus 5 means it is 1 by r power 5. Radius is coming down. When the radius is coming down, the resistance, the rate at which resistance is increasing is 1 by r power 5. Still worse. So what is killing Dr. Sundar is this power.
Yes, sir.
That is what is killing in this whole thing.
Yes. Yes.
Is that clear? Dr. Shanti, so dr by dt, it is decreasing radius. So which means that dr by dt is negative. So there is one negative here, one negative here. So it becomes positive. Actual rate is d resistance by dt is positive. Okay.
Yes, sir.
Yeah. So that is why you have vasodilator, you have, this radius business is the most important. Okay. So when you want to increase your blood pressure, vasoconstriction, reduce it, and so on. So that's why radius plays a very important role. In fact, we were trying to find out how much, the resistance actually changes. It's a very interesting factor. How much actually reduces, the resistance changes. Because all the resistance change they don't take place to that extent in iota. There's more in arterioles because R is the factor. Okay.
How do you, this is an ideal situation. So the radius is going to vary in different areas. So
Dr. Shanti, I'm not able to hear you. Is anyone hearing Dr. Shanti? Can you? Voice is very weak. Very.
now, okay, I'll just type my.
Can you type it out in that chat and someone read it? Can you read? Just type a message in that. Let's read it because I'm not able to hear your voice. Is anyone hearing? Maybe I'm using iPad. Is there anyone hearing?
She
No,
has
sir,
sent a
there is
message.
some sort of airflow kind of.
So
Yeah.
she has sent a message, sir.
Can you read the message?
Sir, when radius is varying, also how is it obeying the law of flow?
The radius is changing.
What
So,
to do?
but when the radius changes, so there is a variation in pressure. If Q is the same, there's a variation in pressure, or if Q is if pressure now because resistance changes, pressure is not adequate, then Q will not happen. So one of the things further would be interested in is what is the drop in pressure further down when there is a plot, right, Dr. Sundar? For the same Q. So suppose this is the plot. So the radius now has changed. The resistance has now changed like this. So between this point and this point, what is the pressure difference, P1 and P2? Say for example, for value Q. Dr. Sundar, is that an important parameter? Hello? Hello? You're able to hear me?
Yes, sir. Yes, sir.
Yes, sir.
So, Dr. Sundar, is the question, there's a question valid? P1 and P2, what is the pressure downstream, right?
Yes, sir. Yes, I'm not able to get you, sir. What is that?
No. The question is, if see, this is the plot. Oh, sorry.
Yes, sir.
So this is the plot.
Yeah.
Okay. Because of which the radius has dropped.
Yes, sir.
So the radius has dropped. Let's say that is the length and so on. So when the
Yes.
radius has dropped, the resistance has gone up.
Yes, sir.
So if there is the flow is say Q,
Yes.
then this P1 minus P2 should increase. Then only Q will go.
Exactly, sir.
So further down the plot at this place, the pressure will drop. This P1 is decided from what is coming in. So this P2 will drop.
Yeah.
And your
It's more of
concern
a
is
fractional flow reserve, like you are coming
yes,
to.
exactly. So that is how we get the fractional flow reserve concept,
Yes. Yes, sir.
right?
Yes.
And you are supposed to put the stent based on this difference, or
Yes.
how
Yes,
much
sir.
it's
Yes.
dropping,
Yes. Yes. That
right?
P1, we can take it as a central aortic pressure also.
I will take
So that.
exactly,
Yes.
exactly. That's the input pressure that's coming.
Yes.
So you can see how the plot, this equation becomes very interesting because that's what will decide P2.
Yes, sir.
Okay.
Yes, sir. Yes.
Dr. Shanti, so this is how you use this equation. So now what am I trying to say? I'm trying to tell you like why certain things are very important. So 90% block, what does it mean? dr by dt is coming down drastically there. So R is actually very, very small. Very, very small. So further flow after P2 is going to be very low because there's no pressure to drive it further. Okay. Okay, fine. So I have to go to the second derivative. Maybe we will do that in the next class. It's 8:35. So no further questions. Is there any question I'll answer, or we will meet in the next class? Next class. See, I have to compensate 1 or 2 classes. Okay, it doesn't matter to us even if we.
I have a doubt.
Yes. Yes.
So when the radius decreases, the pressure increases, right? Like.
Yeah. So if the radius decreases, the resistance increases. When the resistance increases, if the flow rate Q is the same, then the pressure has to increase. The pressure means is the pressure difference, upstream, downstream.
Okay. So P1 increases.
P1 is usually, as Dr. Sundar said, it is the central pressure, aortic pressure.
Okay.
P2 is what will change now.
Okay. Okay. So to the pressure difference increase, P2 has to decrease.
Decrease.
Okay.
Is that clear?
Yes, sir.
Dr. Sundar, am I correct? You are the expert. You are the boss.
Yes, sir, you are right, sir. Actually, the P2, what Dr. I think Arjun asked was because naturally when the artery get constricts, naturally we think of increase in the flow. For example, when we press the pipe of hose pipe, then naturally the flow increases and it goes beyond that. So here, the mechanism what we follow in fraction flow reserve is we always vasodilate the microvasculature, everything. Those distal pressure we neutralize, no sir, in the microvasculature, and the P2 will get neutralized. Normally, what we do because the physiology is little bit different here, because after a stenosis, we'll always have a drop in pressure, there will be a vasodilatation, there will be the arterial, there will be a regulation by the body that normally the segment what sir has marked as a P2, there will be a little bit dilatation in the artery too. There will be the resistance of that artery, that part of artery will get decreased after a stenosis, because of that auto regulation. Normally this P2 will be always less than P1 here, sir.
No, P2 you should always be less than P1, then only Q will go.
Exactly, sir. Exactly. I am explaining why the P2 is less with all the auto regulation part, everything it will be there. That's why.
So now, how does that happen? Let us understand auto regulation.
Yes, sir.
Let us understand auto regulation. So now, what is auto regulation? Now that is the radius further down, right? That radius will increase. Correct, Dr. Sundar?
Exactly, sir. Yes, sir. Yes, sir.
So now come back to this equation. So what is happening now? dr, what is happening to dr by dt at that place?
Increases.
That increases. So that means that negative is not going down. So there is negative here.
Exactly, sir. Exactly, sir.
So the resistance actually drops because the change in resistance is now negative.
Yes, sir.
Okay.
Yes, sir.
Right. In fact, one of the most difficult things to model is this auto regulation, because
yes,
the auto regulation is understood, but there are constants in that, even baroreceptors, for example.
Yes.
If you look at it, there are that constants vary from one patient to another. How much that auto regulation is acting, it's not a constant for people, right?
Yes, sir. Yes, sir.
So it may vary from one person to another. It's a very complex
I
problem.
wonder how. Yes, sir.
Yes. Please.
It's very interesting to see, sir, because I am from this. I am explaining from the medical side. You just put a formula and explained everything in that art regulation in a single formula. That is very wonderful to see that.
Yeah.
Yes. That P2 part, even though we explained with that the auto regulation, that when I see it in the formula, it is very stunning, sir. It is surprising when you explain that formula.
It's very simple, actually.
Yes.
Okay.
Yes, sir.
Great. So we'll continue this in the next class. So I want to use the formula, for example, in branching. You know how what is the effect of branching? All that. We'll go step by step. We will look at this. This is very straightforward, simple things, but so much of explanations can be given with this. Yeah. Thanks. Thank you. So we will.
Thank you,
we'll
sir.
meet.
Thank you, sir.
Next class. Yeah. Thank you. Please.
Sure, sir. Thank you, sir. Thank you, sir.
We will.
Next class will be this week or sir next week?
Because Dr. Sundar said we need some preparation. So we'll meet next Monday. See, I am not in a hurry to finish it. It's not that we need to finish it by April 24th or something. I can take a few more days also. So please revise everything. We will meet on Monday again.
Okay, sure.
Okay?
Sure.
Yeah. Thank you.
Thank you, sir. Thank you. Thank you, sir.
One small information from my side, sir, to the class
Yes,
group.
yes.
The folder where I have been uploading the recording videos will no longer be accessible for me in March once. I will upload it in a different location and I'll be sharing it to everyone in the new group. So I just
Yeah,
want everyone to be aware of it. I'll also write a
Sure.
message on the same in the group.
Yeah.
Thank you.
Thank you,
Sure,
sir. Thank you.
sure,
Thank
sir.
you.
Thank you. Thank you. Thank you, sir. Bye, sir.
Thank you, sir.
Bye, sir.